Hi there, the purpose of this video is to conduct a cost-benefit analysis of a renewable energy solution for a factory which demands 3 gigawatt hours of electricity per annum. Cost-benefit analysis will be undertaken via a levelised cost of energy analysis. The factory will have a 20-year lifespan, which means over that lifespan it will consume 60 gigawatt hours of electricity. The assumption for our analysis is that the factory can use all the energy generated in real time. So there's no battery storage. 3 gigawatt hours per annum energy or electricity demand. Energy is power times time. Number of hours in a year, 8,760 hours. If we divide our energy by the time, the number of hours in a year, then that comes out to be an installation, a power requirement of 342 kilowatt power installation. That assumes that we could generate that power 24/7. If we take into account load factor of various renewable energy systems, for biomass energy system we're using a load factor of 70%. So what that means is for those 8,760 hours, only 70% of the time can we actually generate electricity, which means that our installation, the power of our installation in terms of biomass would have to be 0.49 megawatts. If we round that up to 0.5 megawatts for the purpose of comparing it with wind and PV. Wind, we're using a load factor or load capacity of 25%. If you do the calculations based on 3 gigawatt hours, that installation needs to have a power rating of 1.4 megawatts. A similar PV installation at 10% load factor, so that's 3 gigawatt hours divided by 876, as in 10% of the time, requires a power installation of 3.4 megawatts. So we can see here, as the load factor reduces, the power rating of the installation has to go up. Just to be clear about load factor and efficiency, efficiency is separate from load factor. Load factor is how much time you can actually generate that rated power. In terms of raw energy out versus energy in for biomass, we're talking system efficiency of 40%. That comes down to the Rankine cycle for an internal combustion engine. If we can use the waste heat output from the internal combustion engine, the steam engine, and we have energy out in terms of electricity plus heat, we get the combined heat and power energy efficiency up to 80%. So the heat could be used as a community benefit. So we're talking about system efficiency going from the chemical energy in the fuel to heat to mechanical to electric out. Similarly, for a wind turbine, if we're doing a comparison between biomass, wind and PV, we're taking the kinetic energy out of the weather system to produce electricity. There is a BETS limit in terms of how much energy out of the air you can extract into the blades. It's 59%. We have losses through the gearboxes, generator losses in terms of copper losses and iron losses. So as an estimated figure, there'll be a 40% efficiency for a wind turbine. Similarly for biomass, we're talking about the efficiency of taking the electromagnetic radiation from the sun and converting it into DC electricity. So for monocrystalline panels, we're looking at 20% efficiency. The one thing with PV panels is they do degrade. If you look at the figures, you can work out that approximately 0.2% reduction in efficiency per annum. So after 20 years, if you start off with efficiency of 20%, the efficiency of the panel after 20 years will go down to 16%. If we conduct a cost-benefit analysis, we're looking at levelised cost of energy or levelised cost of electricity, which is defined as the sum of the costs over a lifespan divided by the energy generated by that technology over that lifespan. And what we want to do is to compare PV, biomass and wind with conventional energy sources such as coal, gas and nuclear. Wind and sunshine energy sources are free, clean, renewable and sustainable. However, harnessing those energy sources is definitely not free, and that goes for fossil fuels as well. They're free technically in the ground, but in order to actually use those energy sources, you effectively need to mine them. So oil and gas may well have good, reliable sources, but they may be questionable in terms of their renewable and sustainable credentials. Fossil fuels do have the advantage that they're energy dense, and with secure supplies they can provide dependable and predictive 24-hour supply, as in the national grid as it's set up just now. So wind turbine, we're talking about life cycle costs. So in order to create a wind turbine, we have to manufacture the carbon fibre blades, we need steel, we need concrete for the construction, we need to put it on site, we need to install it. It's going to operate giving us renewable clean energy in terms of the fact that there's no fuel costs, and at the end of life we're going to recycle it if at all possible, so it has a full life cycle, and we want to take account of that life cycle in the levelised cost of energy. If we review PV first, we're using a load factor of 10%. Footprint will be relatively high for an installation of 3.4 megawatts, which on today's prices in October 2020 has been estimated at £3.4 million for an installation of 3.4 megawatt power. Maintenance I've got down £10,000 per year. You're going to have design and project management costs, you're going to have decommissioning and recycling costs. Fuel will be zero. If we add up all of those costs, it comes out to be £3.8 million. We divide it by the energy we're going to get out of that system, as in 60 gigawatt hours. If we do the calculation, it comes out to be a cost of £63 per megawatt hour. So £63 per energy. If we do wind, similarly, using this load factor of 25% for our 3 gigawatt hour per annum, we need an installation of 1.4 megawatts. Using current costs, they're estimated to be 1.4 million capex and installation costs. Maintenance costs may be relatively high. There's an estimated figure there over 20 years of £1 million. Design, decommissioning costs, zero fuel because we're using the weather system. If we add up all our costs, it comes to 2.6 million over the 20 years. Divided by the energy we'll get out, that's got a cost of £43 per megawatt hour. Similarly, if we contrast it with biomass, do the same calculations for 0.5 megawatt installation to give us that 3 gigawatt hour per annum, 3 gigawatt hour per annum energy out. Estimated cost to buy the biomass steam generator and install it is £1 million. Maintenance, design, project costs, fuel costs is critical to biomass. That's been estimated at £1 million over 20 years. If you do the calculations based on these estimates, it comes out to be £43 per megawatt hour over that lifetime. I would accentuate that these are estimated figures. So wind and biomass costs are the cheapest. If we compare them from our figures, we've got PV at 63, wind and biomass come out to be the same, and if we compare them with coal, gas and nuclear, that would suggest that on the face of it they are economically advantageous to implement renewables. However, renewables are intermittent, they're weather dependent. If you don't have any battery storage, then that may not necessarily be the case. We're not taking an account of intangible benefits such as renewables. When they're generating, they have zero CO2 emissions. We're not taking into account any intangible costs of social cohesion and benefits to the community at this stage. If you can arrange to use PV energy in real time when it's sunny, or wind energy when it's windy, and switch back to the national grid when the weather does not suit, then you don't need any battery storage. However, you will still have to pay the additional national grid prices. The levelised cost of figures will stand as per the table there, as you're still using that power generation from renewables in real time. However, your overall energy costs will increase significantly because you're connecting to the national grid when it's not sunny and it's not windy. To provide 24/7 power on demand solely from intermittent sources like PV and wind, storage technology is required, which is expensive and will result in your levelised cost of energy for renewables to go significantly higher. If you can arrange all your demand to align when it's sunny and when it's windy in terms of using that real-time generation, your levelised cost figures will be accurate and valid. However, that's unlikely to be a pragmatic situation. You would need to arrange your life around the fact that you can only use that generation at particular times, which is dependent on the weather. If you require 24/7 energy, then battery storage is required. Batteries cost money. They require significant mineral and energy resources to mine. There's questionable environmental impacts and sustainability issues. They require footprint. They require areas to mount them in. They will have maintenance costs, and their lifespan may also be limited to less than the lifespan of the actual installation, which we've got down as 20 years. If we do a comparison with lead acid and lithium, based on the current figures we can get off the internet, with a lifespan of 8 years, and taking the lithium ion batteries and scaling it up to our 1 megawatt hour battery storage requirements, based on the information we can get, then that battery installation to give you 1 megawatt hour delivery from batteries would cost £0.5 million. However, if we have to replace these batteries, say 3 times over a 20-year period, then the cost at current prices would be £1.5 million. So we're going to then redo the levelised cost of energy for wind to include the 1.5 million battery to make it more pragmatic for the factory. If we include battery costs, £1.5 million over the 20 years, then the original figure is significantly increased up to £68 per megawatt hour with battery storage. Based on information that's out there from Bloomberg, they have benchmark figures showing battery storage significantly increasing the costs of renewable energy. So one caveat when looking at levelised costs of energy through academic papers online or in books is, do they include battery storage or not? If you include battery storage, then your levelised cost of energy for PV and wind is significantly higher than without it. So the question may arise, what may be the best combination of technologies in terms of renewable technologies for your factory, taking multiple factors into account? So these are just some of them. It may almost certainly be not pragmatic to power a factory with just wind or just PV, or indeed a combination of the both. Why? Because these technologies by default are weather dependent, they're intermittent, and hence they're unreliable sources of energy. And how are you going to overcome that? If you overcome that with battery storage, then your levelised cost of energy figures based on this basic analysis significantly increases. And that, on pure economic cost grounds, would suggest that that's not economically sensible in terms of just comparing it with fossil fuel generation from the grid. The most pragmatic solution may be to install wind or PV plus biomass, or wind or PV plus the national grid. Why are we suggesting that? PV and wind provides the intangible benefit of security of supply. So to some extent, if you can come off grid, you know that you're going to have security of supply, and that may well give you the intangible benefit of its essentially peace of mind, and it does give you the tangible benefit in terms of costs of insulating you from continually rising national grid prices. Biomass is an attractive economic solution, providing you have low fuel costs. Being solely reliant on the national grid has risk factors in terms of if you have blackouts and the grid becomes unreliable, particularly at times like these, due to the question mark over the dependability and the cost of gas, which is a significant part of the national grid electricity generation. So most days, if it's not windy, it takes you up to 50% generation required from combined gas cycle generators. And it does protect you from the known unknown of rising prices. Thank you for watching. Please put any comments in below the video.